it over to Chris and let him go over developing microservices.
Yeah, it's funny. I'm not sure how extraordinary I really am, but for the next 40 minutes, I'm going to try and stand in one spot and just speak into a microphone, because I'm really bad at speaking and holding a clicker and holding a microphone at the same time. So this talk is sort of basically about Scala-flavored microservices. So a large part of the microservice architecture is really, it really is just architecture, and it's very much language neutral. But at some level, of course, you've got to get down into code. And so, in this talk, I'm going to sort of talk about how and why you should build microservices using domain-driven design aggregates. And then I'm going to show how you can implement those aggregates in Scala, because sort of Scala adds this sort of functional flavor to things. And so the aggregates are implemented using Scala type classes. So for those of you who don't know me, I'm Chris Richardson. I got my start in programming back in the 80s and spent the first 7 years of my career building Lisp systems, Lisp, of course, being an early functional and then object-oriented language, and then eventually ended up programming in Scala, wrote the book Pojos in Action, which is all about Spring and Hibernate. So that was 10 years ago. 9 years ago, I started tinkering with this obscure service known as Amazon EC2, back when it was in beta. We were shocked at the Oakland Jug to find that they had APIs for provisioning servers, right? Take it for granted now, but back then it was mind-blowing. So much so that I created a startup called Cloud Foundry, which was then acquired by SpringSource back in 2009, right before SpringSource was acquired by VMware. So I was part of SpringSource VMware and then Pivotal for 4.5 years. And then I left about 3 years ago. So now I just sort of do everything related to microservices. So just sort of, living the microservice dream, not really. So I do consulting and training, and I also have a startup called Eventual, and we're building a platform to simplify the development of transactional business applications using the microservice architecture. And if you want to know more, go to learnmicroservices.io, and there's just links to articles, presentations, example code, and a whole bunch of good stuff. Okay, so I want to first sort of set up the problem that I'm going to solve by talking about how there's really a mismatch between the microservice architecture and how we normally develop business applications, right? So the microservice architecture, in a nutshell, is a way of tackling complexity by modularizing the application. And in this case, the modules are services which have these impermeable boundaries. You can't break encapsulation. And so, you architect a system like this where there's a whole bunch of services, each rep is implementing a particular business capability. And there's this distinctive characteristic of the microservice architecture. Namely, each service has its own database. Its data is private to it and can only be accessed through its API. And that's really, really important because it enables loose coupling between the services. So teams can work autonomously on their services without having to coordinate schema changes with other teams. But it actually creates some real problems. So sort of the microservice architecture as a whole has a bunch of sort of challenges. And then that functionally decomposed database architecture creates problems as well. So number one, if you look at a typical domain model, like here we've got orders, customers, and products. The objects just reference one another, right? That's the essence of the domain model. So patterns, so orders have a reference to a customer, and order line items have a reference to a product. And that's perfectly normal. The trouble is when you want to put orders in the order service and customers in the customer service and products in the product service, you've got these things that are sort of object references. And by definition, object references cannot go across process boundaries. So there's sort of this mismatch between the domain model and microservices. Another problem that you run into is traditional business logic relies heavily on ACID transactions, right? So in this case, we want to verify that we want to create an order, but before we do that, we want to verify that this new order will not exceed the customer's credit limit. And so that's trivial, right? You begin a transaction, you find the existing orders, you find the customer credit limit, make sure there's enough credit, and then you insert an order and you commit the transaction. And the ACID properties of transactions guarantee that even if there are simultaneous attempts to create an order for the same customer, that business rule will never be violated. You know, ACID transactions basically are serialized at some level. So it's really simple, and we just sort of take it for granted. But there's a problem. Orders belong in the order service. Customers can't belong to the customer service. So you can't write sort of transactions that access data in this way. And if you did, it would require a distributed transaction that would span the order service and the customer service. And for a whole bunch of reasons, modern applications do not use distributed transactions. It's just sort of not the done thing anymore. And there's sort of a whole bunch, I mean, obviously it will work subject to a whole bunch of fine print, but there's a whole bunch of problems that you run into, both sort of practical in the sense of how distributed transactions work, and sort of issues around performance. And then, of course, there's this fact that many modern technologies don't support distributed transactions, right? Pick your favorite NoSQL database. And then there's the CAP theorem that says you basically have to choose between consistency and availability. And people prefer available systems over consistent systems. So it's sort of like isn't an option in modern applications. So it's like our domain models our domain models resist decomposition, and transactions also resist decomposition as well. So what can you do about it? So one part of the solution is to use a concept from domain-driven design known as an aggregate. So this really is a must-read book, even though it's sort of a relatively ancient text being written back in 2003, 2004, and it has nothing, microservices sort of obviously in a sense didn't exist back then. It's packed full of useful design techniques that are incredibly useful when building microservice architectures. And it's it's a whole bunch of different techniques. But one of them is this aggregate concept. And what's interesting is an aggregate is part of the building blocks of domain models. So there's sort of ways of structuring your domain models. And some of those building blocks, like entity, value objects, and repositories, have pretty much entered everyday developer vocabulary, right? I sort of read that, 10 plus years, 15 years ago, and said, yeah, sure, I'm going to build systems with those components. And then there was this aggregate thing, which had very sort of, arguably, these philosophical motivations for using it, and I just ignored it. Like actually all of the useful stuff in DDD, turns out I ignored, and now I'm paying attention to. But it turns out aggregates are really an incredibly useful tool when writing domain logic for a microservice application. So an aggregate is a cluster of objects that can be treated as a unit. So typical business objects or business entities like an order doesn't just consist of an order. There's some other objects in there as well, like order line item and say address and payment information. And collectively, they form what is called an aggregate. So it's a way of basically modularizing your domain model. Instead of it just being a mass of interconnected classes, it really is a set of interconnected aggregates. So that's kind of good in a sense, and sort of just says, well, this is the scope of an order. But aggregates go beyond that. And that's because they have to conform to a couple of different rules. So one of those rules is that references between aggregates can only be in terms of primary key value. So in other words, an order does not have an object reference to a customer, it has a customer ID. Likewise, an order line item doesn't have a reference to a product, it just has the product ID. So, so within an aggregate, you can use object references, but between aggregates, you can only use primary keys. And if you're used to just traditional object-oriented design, this would be considered a sort of design smell. It's just something that you never ever did. But in DDD you do, and it turns out that in a microservice architecture, this is really, really important. Because now your domain model is made up of aggregates that have very weak connections between them. No longer object references, but just primary key values. So then that makes it really easy to put an order in the order service, a customer in a customer service, and the product in the product service. So it enables you to decompose your domain model. So it's great. So you go read this ancient text on aggregates, and you can apply it to modern application architecture. But wait, there's more. Another rule is that a transaction can only create or update a single aggregate. And when I read this, it just made no sense whatsoever, right? Like I was using I was building monolithic systems, I had a relational database, and so I could begin a transaction, update whatever I want, and commit the transaction. And then there was this crazy book saying, no, you can only update one thing. And then once again, there were these sort of philosophical motivations for this. But if you think about it, this is great in a microservice architecture, because if you have an aggregate within a service, then a transaction will, by definition, be local to that service. So we've sort of solved this problem where we've eliminated transactions that span service boundaries, which is really, really useful. So it's sort of like, yes, this book that had philosophical motivations for saying this is now solving addressing a very deep technical constraint in a modern architecture. And not only that, it actually fits with how NoSQL databases work, because they don't have ACID transactions as well. So it kind of kills two birds with one stone in a sense. It fits with the microservice architecture, and it fits with NoSQL databases as well. So that's aggregates, right? They give you the tool to design business logic that fits within the microservice architecture. And later on, I'll show some Scala code that implements some aggregates. So that's one problem taken care of. The other problem is that yes, we've broken things up, but we still need a way of maintaining consistency across services, or in other words, between aggregates, right? So, because earlier I showed the example of how to, we need to enforce this business rule that says this credit limit business rule. And if your system is decomposed, and how are we going to do this without two-phase commit? How do we do this between aggregates? And the solution is to use basically an event-driven approach, which you could call which goes by the name of a saga. So instead of a distributed transaction that's spanning multiple aggregates and multiple services, instead you're going to use a saga that is a sequence of local transactions. And for the credit limit case, it's actually a transaction in the order service, and then a transaction in the customer service, and a third transaction back in the order service. And each transaction emits an event that triggers the next transaction in the sequence. So that's the architecture. So distributed transactions get replaced by event-driven sagas. So the way the order checking, the credit limit checking would work is an order gets created in sort of this pending state. It publishes an event saying the order has been created. That gets consumed by the customer service, which then goes and reserves credit for that order. And then it will publish an event indicating the outcome of that credit check, namely either the credit was reserved or the credit check failed. That event gets consumed by the order service, which will then either approve or reject that order. So we've got this, event-driven, eventually consistent workflow that's spanning multiple services and maintaining data consistency across them. So that's the new model. So we've got aggregates, and we have these event-driven sagas. And it's not, it's a little bit more complex, right? So one example is, if you think about ACID transactions, when in the middle of an ACID transaction you find out that a business rule is going to be validated, you just roll back the transaction, and those updates are basically undone. It's as if they never happened. Whereas in this model, you have to write code to explicitly undo what was done earlier in the saga. So for instance, in this case, right, an order was created, but the credit check was failed, so we have to cancel the order. And another sort of more elaborate example is when you're transferring money between bank accounts. You've debited one bank account, and then you try and credit the to account. You actually have to undo the debit, and if the to account is closed, you have to undo the debit by recrediting the from account. So you have to explicitly roll back. So that's a design challenge. And then another challenge that is sort of a more technical challenge that you run into is, in order for this saga mechanism to work, you need the underlying infrastructure needs to be able to atomically update the database and publish an event. Both of those things have to happen in order to ensure correct working of your system, right? Because, for instance, if you created the order and then crashed before publishing the event, that order would just be left hanging, right? The next step would never happen. So those two things have to happen together. And what's ironic about this is that the normal way of achieving this is to use a distributed transaction involving your message broker and your database, but we can't use that. So we end up having the sort of the underlying mechanism has to work in a different way. And there's a few different mechanisms that you can use. So one of them is actually, it's like in use at some companies like LinkedIn. They actually tail the database transaction log and commit log, and then when looking for changes to tables, and then those changes get published as events, which can then trigger the next step in the saga. So there's a few different options there. But my personal favorite is one that's called event sourcing. And that's an event-centric way of both persisting your aggregates, but also an event-centric way of sort of structuring your aggregates as well. And it basically uses events for everything. So rather than having to update state and publish events, all you're actually doing is basically saving events in an event store, which also publishes them as well. So we get rid of the state, now is consisting entirely of events. And the way that works is, for every aggregate, you identify the state-changing events, define event classes, so you sort of model them as first-class citizens. So for an order, it would be order created, cancelled, approved, rejected, and so on. But then you actually persist the events in the database. So you could imagine, instead of an order table and a customer table and a product table, in a very sort of simplified form, all you have in your database schema is an event table. And so whenever the state of a domain object changes, you simply save an event into this table. So when an order is created, you insert an order created event. When it's approved, you insert an order approved event. And then when it's shipped, you insert an order shipped event. And this is how you now store the orders. So there's no separate order table. And then when you need to reconstruct the state of an order, you just query the event table, load its events, and replay them, which in a functional sense is doing a functional fold over that stream of events to reconstruct the current state. So it's a very different way of sort of doing persistence. And there's actually a whole bunch of benefits to doing things this way that I don't have time to go into. But you can basically think that this event store is basically a hybrid of a database, because you can insert aggregate events and retrieve aggregate events. And it also acts as a message broker because you can subscribe to the events as well. And there's a few different implementations, including like Lightbend have Lagom. Got to pronounce that right. And also my startup is building one as well, and there's one in .NET land as well. So that's sort of the model. So we've got aggregates that are persisted using event sourcing, which generates the events that can be used to trigger the next step in a saga, and then maintain data consistency. So very, very different model to the sort of the traditional ACID programming model, but you have to do something like this if you want to build transactional business applications using the microservice architecture. So that's sort of the theory. And now we can actually look at some code. So one of the examples is this, well, it's the customer and order example. So there's a customer microservice that hosts the customer aggregate. Whoops, there's the order service that hosts the order. And there's some other pieces in there that I will explain in a minute. And then the third service on the right is actually the order history service that is subscribing to events that are coming out of the customer service and the order service and updating a materialized view that sort of got kind of customer order history. And that's using a technique known as CQRS. And then there's this mysterious thing, Kafka command bus, because Kafka's cool, so you have to have it in there, of course. But there's actually a good reason. So it's a little bit more elaborate than the model I've described so far. And in a minute, I'm going to talk about why it's a bit more elaborate and why I'm using Kafka. And why in here are these other things? There's not just an order. Okay, so there's a whole bunch of different ways of implementing aggregates. So the Java way would be using mutable, sort of traditional mutable, sort of object-oriented classes. Scala, of course, is all about functional style code. And so the aggregate model here is based on type classes. So like an order, that is actually going to see this is a case class that's got the state. And then the business logic of processing commands, which yields events, and applying events to update state is actually implemented by an order aggregate type class. So in the framework, there, for instance, there's an aggregate trait that captures the essence of representing state as a sequence of events. So there's a new instance member which creates a new instance of the state, and an apply event method that takes the state and an event and gives you an updated state. And then there's an apply event method that's doing a functional fold. So this aggregate's representing the concept of, or this aggregate trait is representing the concept of reconstructing state by folding events. And that's actually used by the event store when you load an aggregate from the event store. Oh, and there's this abstract member called aggregate event, which says for this aggregate, this is the particular class type of events that it supports. And the implementation of this aggregate will, define the concrete type. So the event store has like a simple kind of CRUD API that's parameterized by the aggregate type that is T in this case. And then there's command processing aggregate that builds on aggregate and adds in the concept of processing a command. So a command is a request to create or update an aggregate. And so there's an abstract type member aggregate command that is the type of commands that this aggregate supports. So those are the kind of the abstract framework level traits. And then here's the order aggregate. There's a whole bunch of stuff in here. So there's like an enumeration. Here's the order state. What do I have highlighting? Yeah, so here's the case class for an order. Here are the commands that the order responds to. And then here is the order aggregate type class. And it says for this order, the type is order command, the event is order event, and here's the implementation of the method. So new instance just creates a blank order, and then we'll have a look at process and apply. So here's the process command method, which is taking an order and a command, and it's just using pattern matching to generate a sequence of events. So the business logic here is really trivial. So there aren't any business rules in here, so it's sort of not doing anything particular interesting. But other than saying, for a create order command, return an order created event. So it's kind of swapping you got to do this command, and it generates a done this event basically. And apply looks similar, so it's taking an order and an event, pattern matching against them to return an updated copy of the order. So once again, the business logic is kind of trivial, so there's not much complexity here. If you go look at some of the other classes, you will actually see at least 3 lines of business logic in this application, because it actually has to. The class that's keeping track of the available credit actually will say, if there's enough credit, then approve the order, otherwise reject it. So that's there's only one business rule in this sample application. So that's that part. And then if you look at a service that's, say, invoked from the web tier, it's written in terms of this DSL. And so we've got this sort of small amount of code that basically is a shorthand for creating an order aggregate. So we want to create an order aggregate by sending it a create order command. And under the covers is actually instantiating an order aggregate by calling new instance, processing the command that gives you the events, applying those events to update the state in memory. And then it's interacting with the event store to save those events in the event store. So that's a really, really simple aggregate. And you can imagine if there's business rules, the pattern matching would actually look a bit more, there would be some conditional logic in the pattern matching and so on that would be more interesting. Okay, so that's an example of the order aggregate. And I now want to talk about this saga mechanism. So the way I drew it before, it was like this, right? The order service published events, like order created, which got consumed by the customer service, which would then emit, in this case, like a credit reserved event or a credit check failed event. And on the one hand, that's kind of nice, but it does mean, though, that the customer service has to know about all of the events that can affect the credit. Like, so when an order is canceled, it would actually have to get that event and free up the credit that was allocated to that order. So there is, in essence, tight coupling between these two services, which is bad. And so it's actually cyclic coupling, which might be okay, but it might not. It just sort of it's a slightly smelly scenario. So one way of solving this is actually to move the functionality for maintaining available credit into the order service. So what that means is when a customer is created, we actually create an available credit tracker for that customer in the order service. So we've sort of kind of denormalized the data. So the customer so a little bit of data about the customer now resides in the order service. And that actually is quite good, because then the events basically bounce back and forth between the order and the available credit tracker, and all of the knowledge about the various order events that can impact the available credit now just reside entirely inside the order service. So we've sort of localized the knowledge, which is good. And the only thing the only dependency that the customer service now has on the order service is that it would have to subscribe to the available credit changed event so it could keep this field up to date. So we've dramatically eliminated a lot of the coupling between these two services, which is quite good. It's better. But there still is this cyclic dependency. This is still slightly, it doesn't smell as bad as the last slide, but it's still a little bit smelly. So,
what about if you introduce a credit service in between? Which the other two directly talk to the credit service?
Yeah, that's an interesting question. Well, could you introduce a credit service? Yeah, so imagine you'd draw a line here between the two. That you could do that, except that the arguments that I used on this slide would now apply to the credit service instead of the customer service. So you've kind of moved the problem somewhere else rather than solving it in its entirety. So this I feel better about this. There's always different ways of slicing and dicing it up. But if you think about these approaches, right, you could, when it comes to sort of system integration, there's two patterns, choreography and orchestration. This is sort of a choreography-based approach. Yeah?
Quick before we move on from this one, when you were saying that you were denormalizing the available credit tracker into the order service, if you now had some other something besides orders that affected the available credit of the customer, would that also be denormalized into it?
Yeah, it depends. I'll give you an example where you couldn't really do this. So imagine that in addition to reserving credit, you had to also reserve inventory. It would probably be bad to have a replica of the inventory data inside the order service, right? So it's sort of, which approach to use kind of depends on the specific. It's very context specific. But it turns out that on the next slide, I'm going to show a different design that actually solves these problems. By eliminating, basically, instead of this service having to subscribe to events from the order service, this service will actually send commands to the other service as well. So we're replacing, in many cases, events by commands, which sort of inverts the dependency and is cleaner. that is there's some interesting kind of consistency issues that then arise. So part of it is when the credit limit changes here, an event would be published which would then trigger the update of the available credit, the credit limit here. But please don't ask about the issues of how to deal with like the outstanding credit is now greater than the new credit limit, because that's a bit complicated. But let me talk about get to the next slide. So this approach where services are listening to one another's events you could basically describe that as choreography, where there's sort of the flow is distributed around all these different services. But it turns out that another way of implementing sagas is basically to use orchestration. And so you have this basically an orchestration object that's basically a state machine that comes into existence in response to an initial event, like an order being created. It's like, oh, an order's being created, so we need to go and validate that order is allowed. And the state machine actually receives events from aggregates and then sends commands via Kafka, hence the Kafka command bus. So sends commands to other aggregates, or in other words, other services. So instead of the order service publishing an event that is consumed by the customer service, the order service actually sends a command, or in other words, basically invokes an API that the customer service provides. So we're actually inverting the dependency. So the customer service doesn't actually know about the order service anymore. The order service, which makes sense, just knows about the customer service. So you've got this state machine that's actually that itself is actually an aggregate, so it's persisted, but it sort of interacts in a different way. It receives events from aggregates and sends commands to other aggregates. So the flow works a little differently. So we've got our available credit tracker in the order service, and the customer service is over there. An order is created that publishes an event which triggers the creation of this order creation saga. So this little state machine that's responsible for implementing this sequence of updates, it will then send a command. So the triangles are events, the squares are commands. So it sends a command to the available credit tracker telling it to reserve credit for an order. And the available credit tracker publishes an event saying the credit's been reserved. And then the order creation saga consumes that event, sends a command to the order service saying you've been approved. So that will trigger the state change of the order. And then it will also send an update available credit command to the customer service. So this, as I've been saying, this is how the dependencies get inverted in this system. This is basically really invoking an API on the customer service. So it's a one-way dependency at that point. So we now have this sort of acyclic set of dependencies in the system. So it's a slight, I don't know if you'd call this more complicated, but what's interesting is that now the workflow is centralized in one place as opposed to being scattered around the system, which in some cases is simpler. So to me, this is a very promising approach. So I'm going to sort of walk through the Scala code, which currently is very much work in progress. The code doesn't really reflect the state machine nature of what a saga really is, and so it's a little bit more complicated. But basically, a saga is actually an aggregate, so it adds in more behavior. So specifically, the critical behavior is this, which is what's the specification of the state machine. So ultimately, I think it's going to look more like it won't look the same because it's quite different, because the goals are different. But I want to take inspiration from like the Akka state machine implementation. So that's what the code is evolving towards. So yeah, it extends aggregate. The concrete class has to supply a specification of the state machine. And then here's the order state saga class. And the key thing, there's a whole bunch of stuff here, but the key thing is the state machine specification. And then because it is an aggregate, it has to know how to apply an event to update it, to restore its state as well. So that's that other method. So and then here is the state machine, which is not quite right. I'm still working on it. But basically it's saying there's a starting when. So that says create an instance of this saga when an order created event occurs. So we got that part. And then the logic here is saying update the order customer, telling it to reserve credit. Actually, that's the credit tracker now. And then there's this event which is representing the state of the saga. As I said, I want to make this more state machine-like. And then there's other clauses which says, well, when the credit limit exceeded event occurs, then update the order in that way, and then here's the event representing the state change. So hopefully that's kind of giving you a flavor of what it does. So the goal is when an event occurs, update some aggregate, which is actually asynchronously sending a command via Kafka. And then it's generating an event which is used to preserve the state. And so as I said, under the covers, it's sending these commands asynchronously using Kafka. So for every aggregate that you want to send a command to, there is a Kafka topic. And then for every saga, there's a failure topic that will contain a message if the execution of commands fail. So like the order saga sends a reserve credit to the credit tracking aggregate. If, for instance, the customer doesn't exist, it will send back a customer not found message, and the order saga can react appropriately to that, like cancel the order because the customer ID was invalid. So anyway, hopefully I've given you a sense of what kind of the flavor of how sagas work. And as I said, over the next few days, the code should look a lot cleaner. So that's my talk, which is good because I'm out of time. So yeah, in summary, right, aggregates are the building blocks of microservices. Event sourcing is a really good technique for persisting aggregates because it actually fits in really, really nicely with the event-driven saga approach that you're going to have to use in order to maintain consistency between aggregates and between services. So thank you for listening. Hope that you found this useful, and here's some contact info. So thanks.